you didn't really pay enough attention yesterday. So let's talk a little bit about what you have to do for this, because this is the kind of stuff that I'm expecting you to be able to do that's pretty straightforward. If you want the acceleration of gravity, the reminder here is that the weight of an object is mg, the mass of the object times its acceleration of gravity. Now, weight is the force of gravity. So that's going to be the mass of object 1 times the mass of object 2 times g over the separation distance squared. This has got to be equal to mg. Now, if we're talking about being on the moon, and we're looking at the acceleration of gravity, say, on you when you're on the moon, then m1 becomes the mass of the moon, and m2 becomes the mass of you. So m and y for you. This gives us the acceleration of gravity on the moon. Now, if we wanted the acceleration of gravity of the moon when you're standing on it, that'd be a different number. But we're looking for the acceleration that you would experience while standing on the moon. That means the mass of you is unnecessary, just the mass of the moon. So mass of the moon times g over the separation distance squared. And that equals the acceleration of gravity on the moon. What's the separation distance? Well, you're separated by the radius. So you had everything you need on the board. Just throw it together, and you get about 1.6 meters per second squared. All right? That was yesterday. Today we're going to talk about orbits. So it's going to be a little bit different. We talked about basic elliptical orbits yesterday, or the idea of elliptical orbits yesterday. Today we're going to talk about circular orbits. The first example I want to work is one that I think is interesting for a number of reasons. So I want to talk to you about the International Space Station. And I want to give you information about it because the way the information will be presented can be presented a number of different ways, and I want you to be prepared for any of them. So the International Space Station orbits at an altitude of 408,000 meters. So that's an altitude. So in your notes here, be careful when they give an altitude. Altitude is the distance from the surface of the planet to where the orbit is. So when I say that the altitude of the International Space Station is 408,000 meters, I'm saying that this distance is 4.08 times 10 to the 5th meters. That's the altitude of the International Space Station. That's not the separation distance between the International Space Station and the Earth. That's going to be the radius plus the altitude. So if you're given something that's an altitude, you're still going to need to know more information. And more importantly, if you're asked for the altitude, then you're probably going to have to subtract the radius. So be prepared for both of those contingencies. And I've given those in your homework. So practice. But I'd like to find out the orbital parameters of the International Space Station. Before I do, though, can you take a minute and practice and tell me what the acceleration of gravity is at the International Space Station? I have a reason for you to calculate this. And for those of you who didn't get the 1.6 a minute ago, this will be good practice. So find the acceleration of gravity at the International Space Station. It's not 0, and some of you think it is. So we need to make sure we have an idea of what this number is. First, I want to point out something important here. It's not 0. I know that astronauts look like they're weightless, but that's because the vehicle they're in is falling at the same rate they're falling. An object in orbit is falling. It's falling around the planet. It's being pulled downwards and accelerated the whole time. The difference in what makes it an orbit is that instead of falling straight down, they have a tangential velocity at the same time that they're being pulled downwards. So although they are falling towards the planet, they're moving fast enough sideways to get out of the way of the planet. So although they fall downwards, gravity is pulling them downwards, they're moving sideways, so they eventually, although do fall, and they're closer to the planet in one direction, they've moved sideways, so they got outside the planet, or got away from the planet. So they are always falling around the planet. And of course, as they do move around the planet, the acceleration of gravity, which is pulling them downwards in this direction, changes direction too because it's always pointed towards the center. So an orbit is a perfect play between how fast they're moving and the direction of the force on them. But they are experiencing an acceleration of gravity very comparable to what's on the Earth. Not quite the same because they are further away, but it is not zero. So they are not technically weightless. They appear weightless. It'd be the same thing if I put you in an elevator and cut the cable. You and the box are falling at the same rate. So for a short time, you'd appear weightless inside the elevator because you and it are falling together. Until, of course, you reach the bottom, and then you'll discover the hard way that you're no longer weightless. But the only reason we remember that we even experience our weight is because we're experiencing a normal force. Remove the normal force, and you'll feel weightless. But they are experiencing gravity. They are almost their same weight in orbit as they are on the planet. There's just no normal force for them to experience that weight. To be truly weightless, you have to be either at the very center of the universe. We are pulled equally in all directions by all the mass of the universe. Or you have to be far enough away from all objects with mass where there's no force of gravity acting on you at all, which is not going to happen for you. So you can appear weightless, but you never really are weightless. Now, with that, I want to talk about orbits. And orbits are a combination of factors, and I want to tell you what those factors are. It starts out with an understanding that there is an unbalanced force that is causing a centripetal acceleration. That's where an orbit begins. It's an unbalanced force that causes a centripetal acceleration. That unbalanced force is the gravitational force. Now we have two force of gravity. So the gravitational force plays a role here. But we're traveling in a circular path, so we also have an expression for the centripetal acceleration for an object traveling a circular path. It requires a velocity. You have to be moving fast enough to deal with the centripetal acceleration you have. Now, interesting point here, you'll notice I'm using two different values here for r. A capital R here, because this represents the separation distance. And a lowercase r here, which represents the radius of curvature. These don't have to be the same thing. They are only the same thing if the object that's doing the orbiting is very small compared to the object that's being orbited. What I mean to say is, if the center of mass of the system is at the center of the object being orbited, then these are the same value. If that's not true, then you have to keep them separate. So in order to figure out when to use that, and again, it's not an exact, it's kind of a gray area. Generally, if the mass of the planet is much greater than the mass of the satellite, then they're the same value. If that's not true, then you have to keep them separated. And you have to figure out where the center of mass of the system is. We're going to do these problems both ways. We'll do problems where obviously the center of mass is at the center of the system, and we'll do it when it's not at the center of the system so you can see both. But you need to evaluate that when you start a problem. A planet around a star, you're probably going to make them the same. A satellite around a planet, you're probably going to make them the same. Earth and moon, maybe not. The moon's pretty big. When we look at it, it's big. It's comparable to the size of the Earth. It's 1/6 the radius. And it's, I know it's not really close in mass, but it's just a couple order of magnitude away. And it does change the orbital dynamics. The Earth and Moon actually orbit about their mutual center of mass. So if you want the most accurate information, if you're trying to go from here to the moon or back, you probably want to make sure you know exactly where the moon's going to be. So we'll run it both ways. First, we're going to do the International Space Station. And there's one more thing to think about here. This would tell us how fast the International Space Station is going. But if we want to find out something like how long does it take the International Space Station to go around the Earth, we'll probably need one more thing. Right, something that relates the period of the orbit with the size of the orbit. Again, this r would be the radius of curvature. So we're going to do a problem that brings all of these things together. This is how you calculate an orbit. We're going to do this in two stages. We're going to find the velocity of the International Space Station first, and then after we find the velocity of the International Space Station, we're going to find its orbital period. All right, ready to go? All right. So let's start this from the beginning. We want to find the velocity of the International Space Station. So we're looking for the International Space Station as the satellite orbiting the planet. So I'm going to start with net force equals MAC. And for my force of gravity, I'm going to do mass of the Earth, mass of the ISS, times G over their separation distance squared. I'm going to set that equal to MAC, but I'm going to replace AC with VT over R. I'm sorry, VT squared over R. Now, before we progress, which mass is this? This will be the mass of the ISS. The mass we put here is the mass of the thing that's orbiting. Right? This is the one that's in circular motion. So we put the mass of the object that's in circular motion here. I've had a few of you kind of complain or maybe raise concerns that you're not able to get everything down. So your notes are useless to you. This time and this me going slow, this is your time to make sure you put down that this is the thing that's orbiting. This is the part that's going in the circle. So that when you do this on your own, you have information to use and you're not blinded by it. So I'm going to put ISS here. Now I'm going to evaluate the two R's. It's time to do so. Do they represent the same distance? And for this problem, yeah. The space station is really small compared to the planet. So we're going to assume the center of mass of the system is at the center of the planet. So I'll make both of these R's the same. Again, take a second in your notes and talk about why I did that. Maybe write it all out again, showing that you replaced little r for big R, so you know why. Your notes are, I've been helping some folks after school, and your notes are useless to you because you don't tell yourself the things you need to know. And then you ask me those questions. I'm like, we talked about it in class. And you don't like that answer, ever. You give me that look. You talk about a lot of things in class, Mr. Sheldon. Perhaps I should make you make videos about it. Maybe that'll make it better. Little fun song videos. Yeah, no, it must be a lot more fun to be in AP Bio than in physics. We're not going to do any videos. No. It's not going to happen. You can go you make up all the raps you want about physics. We'll see if that makes you able to do this problem. Because I'm thinking the answer is no. But you try. I'll let you guys experiment. That's it. That's what we'll do. So next step, I'm going to cancel out the mass of the ISS. And that's something that's going to happen every single time. So just keep that in mind. What?
Sorry, can you repeat why you switched out little r for big R?
Because you have to ask yourself at some point in this problem if the separation distance is the same thing as the radius of curvature. And that question is answered by asking yourself, is the mass of the thing that's being orbited much greater than the mass of the satellite? If it is, then the center of mass is at the middle, and you can make those the same number. If it isn't, you can't, and you have to find where the center of mass of your system is. Write that down. That's the answer. That's the decision. And I said that it might be hard to make that decision sometimes. You'll generally be told. But right now, our object is very big compared to the thing that's doing the orbiting, so it's easy. So planets around stars, you probably make the R's the same. Satellites around planets, you probably make the R's the same. Go ahead.
And the mass of the thing orbiting always cancels out?
It will always cancel out. Which is good to know because they don't always give you the mass of the satellite. I didn't give you the mass of the ISS from the beginning, so you should expect it to cancel out. Like, if I thought you would need it, probably would have been on the board behind me, right? So let's keep going. We are going to make the R's the same. I will point out that one of the R's cancels out under this circumstance too. That's nice. So I'll take out that one R. And I'm left with mass of the Earth times g over r equals the tangential velocity squared. That's what I want you to find out. How fast is the International Space Station going? I'll give you like 60 seconds because now it's just plugging in numbers. But you need to practice there. And don't forget, this r is not the radius of the Earth. It's the separation distance. So you will have to include the altitude of the International Space Station to get the correct answer. Why do the r's cancel? All right. I have an r squared here and an r here. So I will multiply both sides by r. I know. It's what I said too, but it doesn't seem to matter, does it? Maybe we can sing a song about it. I don't want to spend a lot of time on you guys playing with your calculators, because if I do, we'll be here forever. But that should be how fast you should get for this calculation. And look, if you can't put the numbers in your calculator, I am not helping with that. We are beyond that. Practice. If you really want to get this right, do it separate. Do the top part first and write it down. Stop trying to do everything in your stupid calculator. All right? But I don't have the patience. I can't be patient with calculator stuff. I'm only going to do this because I know somebody in the room has to see it, and it's not great for me. Okay? Now you play with your calculator on your own time, all right? Because we got to move forward. That's fast. Do you have any idea? I mean, you're going to get these numbers that are going to look like this because, well, astronomical stuff is big. And imagine being the folks in the 50s who, they were just hoping that all this Newton stuff was going to work out for them. And then they're going to chuck people into space. That's why they started with animals first. Because to get something to go around the planet at that altitude, they were just going for lower Earth altitudes, to be honest with you, but the speeds are comparable. You have to be traveling really, really fast. I mean, is this really fast? Like, do you have any frame of reference? I mean, speed of sound is 300 meters per second in air, about 333. So if you figure the fastest planes that we've made that have humans driving them, about 3 times that. You start getting into unmanned vehicles, we can get about 5 times that. We want to start getting into stuff that is no longer breathing air and is rocket powered. In the atmosphere, you can't go this fast. It'll just burn up. That's why stuff burns up on reentry, because it's going this fast. It's the atmosphere that destroys it, or it bounces off the atmosphere and goes tumbling into space. This is really fast. So when we talk about docking with the International Space Station, all the videos you tend to see show it nice and slowly and gently coming into the International Space Station, but both of them are going this fast. Right? That's why it looks like it's slow, because it's just going a little bit faster than the International Space Station, but they're both traveling at this speed. It's the only way to remain in orbit. Why do you think it means so much to launch from Florida? We already know that being here is a little over 400 meters per second. That's a heck of a boost when you have to be going 7,600 meters per second. That's why whenever we have you see a rocket taking off, if there's humans on it, it goes way slower. Part of the reason is because the humans can't take it. But if you're launching just, stuff, we can go faster. But they still can't go as fast as they want to. They have to keep the engines throttled down until they get to the upper atmosphere. And then they can throttle them up so that they don't burn up on the way up to the space station. It's amazing that this is the speed. This is how fast they have to go. Now, go one step further and use that to figure out how long it takes for the International Space Station to go around the Earth. This R represents the radius of curvature as well, but for us, it's also the separation distance, which is going to be the value that's right there. We want to take this value and figure out how long it takes. Put it in appropriate units, because the answer you're going to get is going to be in seconds. But again, that might not mean very much to you. a terrible idea for you to figure out how fast the moon is going. I think that's kind of a good activity. But I'd also like you to figure out the period of the moon. But I want you to figure out the period of the moon going around the Earth without finding the velocity first. Don't get me wrong. I want you to find the velocity, because knowing how fast the moon's going should make you pretty impressed with the fact that we can land on it. Because it's not like we're landing on a stationary target. We're landing on something that's moving really fast. But I want to find the period directly, which involves a little more algebra than we had before. So I want to walk through the same exact problem again, but this time we're going to talk about the Earth-Moon system. And at the end of the day, we know it takes 28 days for the moon to go from full moon to full moon. So we kind of know what the answer is going to be. That's why you should practice on your own, because this is one of the only units where you know the answers before you start the problems. Pick the Earth around the sun. You've got the information up here to do the problem. You know your answer should be 365 days. If you don't get 365 days, you know you did it wrong. It's not like it's a mystery and you're comparing it to maybe my incorrect answer key. It's something where you will know what the answer is supposed to be ahead of time and you can practice. So let's do the Earth-Moon system, but I want to do the Earth-Moon system without stopping to figure out the velocity of the moon. So that starts with net force equals MAC. Right? We're still starting in the exact same place. We're interested in the moon's orbit around the Earth. So the left side, mass of the Earth, mass of the moon, G, over separation distance squared. That has to equal, we're looking for the moon's orbit, so mass of the moon times VT squared over R, where R is the radius of curvature. Now I'm going to leave the little r there for now, and we'll evaluate whether we're going to make those the same r or not the same r at the end. But I want to do a substitution first. We know that the tangential velocity is equal to 2 pi r over t, where t is the period. Like I said, I want to solve for the period directly. I don't want to walk it through the velocity first. So we're going to do some algebra here. This derivation has been on the AP exam 3 times in the last 30 years, and it nets you about 4 or 5 points. It's worth doing. So I'm going to do a substitution here. First, I'll cancel out the mass that I don't need, and I get mass of Earth times g over r squared equals 2 pi r over t squared times 1 over r. Now, this is just algebra, but in first period I felt compelled because of some students to do all the algebra steps, and after what I've seen in here, I probably should do all the algebra steps too. But oh boy, it's so lame, algebra. But there's a step. We have to square everything. And although writing this all out every time gets really annoying, here's another step. Cancel out one of the r's. I could cross multiply. Now I can isolate t. And we've done it. Now, you should ask yourself, if the r's are the same. If they are the same, then this would be so maybe not an equal sign here. Maybe I'll put an or here. Because it's going to be one of these. So if you're dealing with a situation in which the center of mass is the center of your system, you can use this one. If you're dealing with a situation in which the center of mass isn't in the center of your system, you're going to have to use this one. And there are plenty of cases where either one of them will be fine. I will point out, I think, something interesting in that this is one of Kepler's laws. If you don't know who Kepler is, so I think all the distances you need are here. Again, we're going to assume that the center of the Earth is the center of this system. So we're able to use this. I want you to figure out what the period is and convert it to days, and we'll verify it against what we think the answer should be.